So just to introduce myself for a bit, my name is Shachar. I work at AWS, and the talk I'm going to give today shares some of my experience for the last year or so. You can see the sample image I have. I generated it using, I forget which AI, and I think it represents well what I'm going to talk about, because you can see what I tried to do there, but it doesn't really work out. And I think that the experience of trying to make FFI and async workloads work together well feels a bit like this. It works. It's not exactly what he wanted to do. So what am I going to talk about today? I am going to talk about, I'm going to talk today about an application. Let's say it's written in another language, higher language, garbage collected language. In this example, it's a Java application. And in that application, we want to call into some asynchronous Rust code. In my example, we have some database client, and that database client calls to the database over a network. It performs some kind of asynchronous operation. That is an operation where you send data and wait for it to return. And we want to send a request from the Java layer of the application to Rust. We want the Rust layer to send a request over the network and get the response, and then pass that response back to Java. Now, this so far is pretty simple. It's being done with FFI daily, but we have a slightly added requirement. We want that after we send our request on the network, that the Rust thread, the Rust logic, would be able to sort of just sit idle and wait for the response to go and do other work. And by the same token, we want also the Java logic to not be blocked either by the Rust code or by the network code, and to go and do something else, so that the Rust code will not be blocked by the network, the Java code will not be blocked by the Rust code. And essentially, this is what we're talking about when we say asynchronous programming, that we run things that allow us to run in a way which is not synchronized, that we're not blocked and waiting until the last thing ends. Now, these days, asynchronous coding is very easy compared to where it was 10 or 20 years ago. Most languages have some kind of, maybe most languages is an exaggeration, but a lot of common languages have async and await syntax that allows us to write a function that mostly looks like a regular function, but in the middle, it uses the await keyword to say, this is a point in which this function will hang, will stop, or will yield control, and something else can run in the meanwhile. And the next line will wait until some condition is met, some kind of external trigger is triggered, and then the next line will run. But the next line behaves just like the next line in a regular function. So we have the async keyword saying, in this function, we might yield control, and we have the await keyword saying, in this line, we actually yield control. And this makes life very easy, because this function does something very complex. You might see the function saying, send something on a network and do something else with a response that you get. But there's also a whole invisible mechanism saying, send something on a network, check if there's other work to do while we wait for the response on the network, perform the other work, receive the response from the network, stop doing the other work, handle the response on the network, and continue to do something. And it's easy to write. It helps us reason about concurrency, about things like I/O, network activity, etc. Asynchronous programming is easier today. Another thing which is easier today is using code written in one language and consuming it in another language. Right? We want the ability to. It's fairly common today to be able to call from one language into another language within the same process. But why would you do something like that? Often you do it for better performance. Now, better performance might be faster code, or it might be code which uses less memory, less computer resources. You write some code in a language where you have a lot of control over your resource usage, such as Rust, C, or C++, and you write your more complex code where you're not performance oriented in a language which might be simpler, such as JavaScript or Python. You might just have a lot of languages that you work in, and you have some complex functionality that you want to write once and then consume it in a lot of languages instead of implementing that complex functionality in a lot of languages and having the potential of differing behaviors of each implementation varying slightly from the others. Or you just might have existing code written in one language, and you have the rest of your code base or your new project is written in another language, and you don't want to rewrite whatever you have. And you don't want to rewrite your existing code. You just want to call into it. So there's a lot of reasons to use calls between languages, and we call this FFI, Foreign Function Interface. Foreign as in something different, something which is not native to your language. Functions are functions. I'm sorry, my phone seems to refuse to shut itself, so excuse me. Functions are functions, and interface saying essentially, this is how it will look. This is the promises we give you. I gave a talk, it's available on YouTube, at length about the concepts and problems in the general case of foreign function interfaces. You can watch it later. Today's talk doesn't assume a lot of knowledge. I'll try to cover the basics in the beginning, but here we're going to talk specifically about the issues with asynchronous programming. Now, one concept that we do need to understand before we go into asynchronous programming is the concept of ABI. We know the term API. API, an application programming interface, is the interface that is exposed to the programmer by a library, by a language, and essentially gives the programmer promises about that interface. It defines things like what functions you have, which arguments the functions take, what's the return types of functions, what the functions actually do, etc. It gives to the programmer promises about the library. And an ABI does something similar, only instead of giving promises to a programmer, it gives these promises to other programs, to other languages, or between libraries too. It defines things such as which CPU registers you use for input or output, what is the size and alignment of structs, etc. And essentially, both these interfaces provide the same idea. They give us the promise that as long as an API or ABI does not change, even if the implementation, the library version has changed, externally you can still use the library, you can still use the code and get the same effect. So an API is an interface. It is the equivalent of an API between languages. And how do we define this interface? Well, commonly today, we use C as the de facto API to be used between languages. So what do we get when we say we use C? It means that when we call between languages, we can pass primitives back and forth, right? Integers, floating points, as long as they're defined in C, we can safely pass them. We can pass raw pointers between languages. I'm not talking here about Rust references, but actual pointers to areas in memory, and functions. But again, not functions such as C# functions or Rust functions, but the equivalent C function. Now, C also allows us to use structs, but in reality, we almost never actually use structs in FFI, simply because higher languages usually have reference semantics and they don't have value semantics, and it's a bit hard to create a struct in a language like Java, JavaScript, or Python. So usually it means that when we talk between languages, we need to be able to talk in primitives, pointers, and free C functions. And the next concept we should understand is marshalling. Marshalling is essentially the conversion of data from one form to another. So if we have a string in C# and we want to pass it to Rust, we need to marshal the C# string into a Rust string. That means that we might need to re-encode it. If it's a garbage collected string, we need to tell the garbage collector not to manage it while it's being handled by Rust. If it's a buffer or a number, we need to make sure that its endianness is correct, because some languages use endianness based on the machine and some have a set endianness. If we're passing functions, we make sure that if I say in C# or in JavaScript, call this function once a computation completes, we give a C# or JavaScript function, we need to convert it into a C function, which is callable from another language. And as I mentioned, we need to make sure that every value we pass, if it's tracked by a garbage collector, isn't garbage collected while we're using it. So these are the basic concepts. We have an ABI, which is essentially what C gives us in order to talk between languages, and anything we pass between languages has to be converted to to a format which is usable by the other language. So now that we put the basic groundwork, let's talk about asynchronous programming. So the first thing to know about asynchronous programming is it's not so simple. You'll see frameworks, you'll see binding libraries which allow you to create functions, asynchronous functions between languages, but the reality behind it is rather complex, and this complexity and the inherent problems are going to be the crux of what I'm going to talk about. I'll cover in very rough lines 3 main issues. First of all, the practical issues. How do we manage threads? How do we manage CPU time between languages? Then I'll explain in a higher level, why do we have these problems? What's the conceptual problem that means that even though we have structures that are meant, as I started, to give us an easy asynchronous programming experience, why they complicate the experience. And then I'll finish with the less basic problem of why performance isn't that great when you use FFI and where's the costs. So without further ado, let's go into the practical problem. So we said we have a Java application calling into some Rust library. And here we'll go down a level and talk about threads, about the actual units of execution running the code. So we have a Java thread, and the Java thread wants to call into an asynchronous Rust computation. It knows that it's going to perform an asynchronous computation, so the first thing it does is creates a future, something that will encompass the computation and will inform the Java framework when the computation is complete so that it can go on, in our example, to the next line afterwards. After it has created a future, it takes the arguments it wants to pass to Rust and marshals them to a shape which is consumable by Rust. It takes the callback it wants Rust to call once the computation completes and marshals it into the shape usable by Rust. Rust receives these arguments, receives the callback, performs some asynchronous computation, sends its data over the network back to the database, receives the response, and in the meanwhile, the Java thread is free to do something else. It doesn't need to wait. The Rust side has received the response. It has a callback. It calls the callback back into Java land. The future is resolved with the response from the database. The Java code can go back and continue its work, and the Rust thread is free to go back and perform the next task or whatever else it needs to do at the same time. And this is the experience we want. But if we do some things incorrectly, if we make mistakes, then there are a couple of pitfalls we should be aware of. The first one is thread exhaustion. If we do everything correctly, Java threads do Java work, Rust threads do Rust work, and as long as each one of the frameworks has enough threads, everything works okay. But if we make a mistake, then suddenly we said resolve the future, the Java future, using the Rust thread. The Rust thread resolves the future, and once the future is resolved, it executes the next command. What executes the next command? The thread which resolved the future. Now, this is because there is nothing inherently different about Rust threads or Java threads. Both of them are operating system threads, and they can be used interchangeably. If we don't remember at the point where we're resolving the future, or if our framework doesn't force us to do that, and if we don't remember to resolve the future and continue with the correct thread, with a Java thread, then we might start moving our Rust threads to perform Java work. And if we do that, then eventually all of our threads, both the threads we allocated for Java and the threads we allocated for Rust, will be busy doing Rust work. And until some thread will come and create a new future and stop doing, until there will be nothing left to do on the Java side, and threads will be released and maybe go back to performing Rust things, the Rust side of the computation will be completely starved. We won't have threads to send requests on the network. We won't have threads to parse the responses, and we won't have threads to call the callbacks, and our program will hang. Another problem that we might have is that we skipped the context switch. That is, in our Java thread called into Rust, but was not released. It is somehow, for some reason, still hanging on on waiting for Rust work, and it is blocked there. And again, this might cause us to exhaust the Java threads because they will all be blocked. Or worse, we might not switch work from Java threads to Rust threads, and suddenly all of our work will be performed on Java using Java threads. And we've halved our available thread pool, and we have some threads doing nothing and other threads doing twice the work. Now, why would this happen? Why would threads do twice the work, and what manages which thread does what? Why do we even need the separation? In order to understand that, we need to understand what allows us to make async programming. And these structures are called, in Rust, they're called runtimes. Each language has its own name for it. So how do we do async computation? What are the basic building blocks that programmers in different languages expect to have? In JavaScript, they're called promises. In C#, they're called tasks. In Python, they're called futures. In Rust, they're also called futures. In C++, they're called futures or coroutines or senders and receivers. But in C, we don't have any such concept. We only have void pointer, a pointer to something. So again, if we remember that, and sorry, but I'll get into the ramification of that later. But what runs these promises, tasks, and future? In JavaScript, it's called the event loop. In C#, it's the task programming library. Executors in Python, runtimes in Rust. I'm really not sure what happens in C++. And again, nothing which is language oriented in C. So what do these runtimes do? They have a pool of ready tasks, tasks which should be executed. And they have another list of tasks which are currently waiting for some kind of external trigger, a response on the network, files to be retrieved from a disk, something like that. The runtime takes a task from the ready list, runs it, executes the commands that the CPU needs to do until it reaches a point where it's waiting for an external trigger. It sent the response on the network, it went to the hard disk and requested that file, and now it puts the task in the waiting list and schedules it to run once the response is received. But after scheduling it, after putting it in the list of waiting tasks, we can go back to the list of ready tasks and get a new task to run. This is our ability to perform things concurrently. The fact that one task is waiting for something that is not within the CPU's control doesn't mean that we should just stop. We can go and find another task which is within the CPU's control and execute it. So in other words, runtimes schedule CPU time between concurrent tasks. They allow each task to run, and once the task doesn't have anything more to do with the CPU, it waits for it, it puts it aside until it will wake up and when whatever it's waiting for will happen. In the meanwhile, don't block the CPU. Use the CPU to do something else. Now, our problem is that runtimes look only at themselves. There is that each runtime assumes it has control of all of the threads. It views all of the tasks. It doesn't know how to talk to other runtimes. And I'll remind you that when we talk about runtimes running between languages, there is no interface which is runtime aware to talk with. If runtimes talk between languages only in C, C offers us no ABI, no concept of asynchronous operations. So there is nothing that allows a Java executor to be aware of the Rust Tokyo runtime. There is no language to communicate the fact that the Tokyo runtime has a task which is waiting for the network. So the reason that we need this slide and have this thread using that resource and calling that thread is because of this. Because there is no higher level ABI for the two runtimes to communicate between each other. A runtime which manages one set of threads can only talk in basic thread speak of whatever the operation provides it with another runtime. It doesn't have a higher level interface to say, I'm awaiting you. This is my promise. Take it as an asynchronous task in your level and complete it. It has to be reduced to whatever C provides us. So this is the conceptual problem. This is why whenever we try to make an asynchronous program that takes the asynchrony and runs it between languages, we will always have to, it will never be smooth. It will never be exactly the experience we want to have, because the interface between the two languages just doesn't have the language which is rich enough to convey the concepts we want. And the final thing is that we could have had, it would have been great if that would be the only problem, but eventually FFI has its cost and asynchrony has its cost. Runtimes have their cost, and when you try to accumulate everything, you get performance which is less than what you would expect. So let's remember that, first of all, everything is allocated twice. If you have a JavaScript promise and it waits for a for a Rust task, then you need to have both a promise and a task. And whatever mechanism the JavaScript event loop uses to track that promise is matched by whatever mechanism the Rust runtime uses to track that promise. All the arguments that we pass, all the return values that we return, they're all marshaled. And everything is managed. If the higher level language uses a garbage collector, then it needs to remember the arguments. It needs to remember the callbacks. It needs to hold everything and track everything. And all of these have costs. And here, in our experience, in my experience, things just aren't as fast as we expect them to be. We expect an FFI call to take a few nanoseconds, but once we add to the allocation and tracking of tasks and promises, etc., things just aren't fast enough. And here I'm getting to the solution that we found, which was to not use FFI for asynchronous computation. When we've, in my work, when we've experimented in single-threaded languages, JavaScript and Python, we found out that we can just send data over Unix domain sockets from Python back to Rust, from Rust back to Python, and it would be faster. But why is it faster? Why is adding more things faster? So what are Unix domain sockets? The first thing to know is that they're also available in Windows. So in case you're wondering about the Unix part, it's not an issue. But they're aimed at passing data between processes, different programs on the same machine. So you take data from one process, pass it to the operating system, and the operating system then passes the data back to another process. This doesn't solve our problem of marshalling, right? We still have to marshal the data, potentially even twice. We need to copy it from JavaScript to whatever format is used by the socket, and then from the socket format back to whatever format Rust uses. We actually might pay more because beforehand we said we need to speak in C ABI in order to speak between runtimes. But now we need to talk in operating system speak. We need to talk about context switches. We need to talk about system calls and kernel calls. And these things are expensive. These things cost a lot. And yet, I'm giving you all these arguments, and yet, for us, they are faster. Why? So my explanation is very simple. A lot of people put a lot of effort into optimizing one-sided communication from Java, from Rust, from JavaScript to Unix domain sockets, from Unix domain sockets back to Java, to JavaScript, to Rust, etc. There's significantly less effort on the specific FFI interfaces, right? Less people work on specifically Java to Rust FFI, specifically JavaScript to Rust FFI, specifically Python to Rust FFI. And this matters because, as we said, the languages, each one of them has unique concepts and an optimization which works in JavaScript and doesn't necessarily work, at least that works when you call from JavaScript to Rust, won't work when you call from Python to Rust. So the fact that you have generalized optimizations and a lot more attention for Unix domain socket might mean that at the bottom line, they're just been optimized further than the specific FFIs. And the Unix domain socket is a generalized interface. It's a stable interface. It's been stable for years. And there's a lot of attention into it. And it's an efficient interface. So I can see practically why it might be faster. But why conceptually is it a replacement? So we've had this slide, right? The Java executor talks to the Rust runtime using C, and I've complained that there is no ABI, there is no language for async operations. But that wasn't true because there is an ABI for async operations. I called it here, I gave it an example, Unix domain sockets, but there is an ABI and it's called the operating system. What do I mean? We said that runtimes schedule CPU time between concurrent tasks, right? There's something to allow multiple tasks to run concurrently at the same time, and the runtimes balance resources between them. And what does an operating system do? Exactly the same thing. It schedules CPU time between concurrent threads, between concurrent processes. And again, an operating system receives significantly more attention and more optimization and more effort than any specific runtime. So if I'm using the operating system as the ABI, as the interface between runtimes, I could get better performance because it's just a better interface. Now, this is specifically our experience, and I can tell you that I specifically said this is our experience when we've benchmarked in JavaScript and Python to Rust. Those are single-threaded languages, at least for now. We've had significantly different results when we've tried using Unix domain sockets in C#, a multi-threaded language, and Rust. So there's a very big your mileage may vary here, but I wanted to communicate the fact that FFI is simply not the only game in town if you want to talk between languages. And there is another system, the operating system, which gives you a very similar concept to async FFI and might be even more efficient. So I have some final thoughts, and then Rainer, if we have time, I have some side points to make. Let's go. So first of all, there's a difference between async framework, right? Runtimes, executors, event loops, they don't only have different names. There's different concepts happening, and concepts, they're built differently, and they don't speak the same language. The core problem we have is that we're trying to convey a simplified async interface, right? Which is, as I mentioned, it's easier in the last 10 years because it is a simplified model of what was once concept. But each language simplifies it differently. And also each Rust runtime simplifies it differently. And this semantic difference is hard to bridge. And it's hard to bridge partly because there is no language that has the vocabulary needed in order to convey these concepts. But we do have something that can convey these concepts, and we do have something with the vocabulary for async computation, and that's the operating system that you can view as a meta runtime. And if I've convinced you that running async futures is complex across languages, well then, async streams with multiple return values, that's a whole nother ballgame. Rainer, do we have time for some small tips and concepts? I can't hear you. I don't know if others can.
I'm very sorry, that was my mistake. My mic was still muted. I'm sorry for that. Shachar, super interesting talk. We already have some questions in the audience, and I have some questions too. But don't worry, take a few more extra minutes if you have extra things to tell us. We are very much interested in.
Okay, great. So I hand-wavingly said that different runtimes have different behaviors and different concepts. And I just wanted to give you one example and one solution to how to bridge that. Rust async futures are lazy. They have the concept of polling. As long as you poll them, they advance. When you stop polling them, they don't advance. If you drop them, they just stop working. They're cancelable. Most other languages have different kind of promises. they have eager promises. Once you start them, once you start executing them, they run. They're uncancelable by themselves. The code in them can just return and stop working, but there's no interface to stopping them. This means that if you try to bind roughly a future to a promise, you might accidentally cancel that future or forget to call that future and thus leave the promise hanging. But there's a simple solution to that, and it's called task spawn. Task spawn takes a future, a Rust future, passes it to the runtime and says, again, in a very simplified manner, run this, inform me when you're done running this, but if I'm not following it, if I drop the handle following it, continue running it. And that makes a Rust future behave roughly like a higher level promise. Another small lie that I said before in my example, I said that whenever we call between languages, we have to marshal a callback, right? You've completed the computation and you need to call that callback. And on every call, you have to marshal a callback. And that could be expensive. And there's a simpler solution. You can make some kind of static callback or a callback per object, but a callback which is marshaled once. And keep that callback alive. Keep a list of waiting futures on the Java side with the Java callbacks, with the callbacks that you need to call back in order to continue the Java computation. And then when you call into the Rust side, you don't need to marshal a callback. You just need to marshal an index into that list. The Rust side, with the callback that was marshaled once, can call that callback with the index. You use the index in order to get the actual Java callback for this specific computation on the Java side and execute it. And essentially, this is an example with callbacks, but the same is true for everything. If you're passing the same string over and over again, don't marshal it again and again. Marshal it once. Keep some kind of pointer index, something like this to it, and use that index, use that pointer. Pass that primitive. And we said that primitives don't need marshaling. They're the API that C provides us. And that will reduce the cost. And that's all. You can occasionally find me on no longer Twitter. And now's the time for questions.